Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 5 of our unit Magnetism and Met. Let's begin with today's class. Today we are going to discuss about the first we are going to discuss about the magnetization and magnetic intensity, and then we are going to discuss about the different magnetic materials. Please attend this lecture very carefully, as this is completely theoretical session, but this theory has been asked in the competitive examination, so I have covered every aspect of the theory and every concept that has been asked up till now, and even those concepts that have a higher probability to be asked. So please listen this carefully. Please attend this very carefully, as well as have a note of all those things which you think that this might be asked in the examination. So let's begin then. Initially, magnetization and magnetic intensity. So when we say magnetization and magnetic intensity, we can say that in a bulk material, the magnetic moments add up vectorically, and they can give a net magnetic moment which is non-zero. This is the situation. Then let's suppose that this is the magnet, and if this is a magnet, and if we see this microscopic view of this magnet, then we can have this kind of situation that this magnet has been made up from so many tiny magnets, and I have represented that dipole moment. So we just have a vector addition of this magnets. While we define a magnetization m of a sample, that can be equal to its net magnetic moment, I mean net magnetic dipole moment per unit volume. So this m, it's a magnetization which would be equals to net magnetic dipole moment per unit volume. This m is a vector quantity, and when I say it's a vector quantity, the dimension would be equals to L to the power minus 1 and A to the power 1. How this has been arrived? Look at this. This is m divided by v. This is I into A divided by v. So this is ampere into meter square divided by meter cube. So this meter square and this meter cube has gone. So this is meter to the power minus 1 and ampere into meter. So it is measured in ampere into meter inverse. Now consider a long solenoid of n number of turns per unit length, and that carries a current I. The magnetic field in the interior of the solenoid can be given as B is equals to mu naught times of Ni. If the interior of solenoid is filled with a material which is having a non-zero magnetization, then the field inside the solenoid will be greater than B naught, and this net magnetic field B in the interior of the solenoid can be addition of this B naught. This is due to the material which has been filled within the solenoid, plus Bm. Bm is the field contributed by the material core, and B naught is the magnetic field due to the external field air. We can say that whatever the current that has been going, and mu naught Ni would be the B naught, and Bm is the field that is contributed by the material core. So now, if it turns out that this additional magnetic field Bm is proportional to the magnetization m of the material, and that can be represented as Bm is equals to mu naught times of m, where mu naught is the same constant that we understood as the permeability of a vacuum, and mu naught having a value of 4 pi into 10 to the power minus of 7, that we know. So it is convenient to introduce another vector field H that we call as a magnetic intensity. Initially it was the magnetization. Now we are defining the magnetic intensity, which can be defined as it's a B by mu naught minus of m, where H has the same dimensions as the m, and it is measured in ampere into meter inverse. Thus the total magnetic field B could be written as B is equals to mu naught times of H plus M. And when I write mu naught times of H plus M, we have partitioned the contribution to the total magnetic field inside the sample into two parts. Let's suppose the first is due to the external factors such as the current in the solenoid, and this can be represented as H, and the other is due to the specific nature. It is due to the specific nature of the magnetic material that we call M. So the latter quantity, the second one, can be influenced by the external factors such as, this influence is mathematically expressed as this M is equals to xi. This is xi. It could be pronounced as xi. It's a xi into h, where xi, it's a dimensionless quantity, is appropriately called as the magnetic susceptibility. What does it? Susceptibility, it is a measure of how a magnetic material responds to an external field. Those materials, those materials, when placed in external magnetic field, external magnetic field tends to become very good magnet, having higher value of susceptibility. So from the value of the susceptibility, you can have an idea that whether this magnet, or I should say whether this material will support the magnetic field or it is not going to support the magnetic field. If the value of the susceptibility is higher, that means this material is ready to become magnet instantaneously. I hope this is clear. Great. Now let's move it. It is small. That susceptibility is small and positive for materials which are called as the paramagnetic, and it is small and negative for the materials which we term as the diamagnetic. So we are going to discuss about the diamagnetic, paramagnetic, even one more materials are there that we call as in ferromagnetic. Yes, but that will be the later part of the session. So let's continue with the relation between B and H. The relation between B and H can be given as, that is equals to B is equals to mu naught into 1 plus xi into H, and this could be written as mu naught into mu r into H, while mu naught into mu r could be written as mu into H. While we understood that mu r, it's a relative permeability, that is equals to 1 plus xi. So mu r, it is a dimensionless quantity that we call as the relative magnetic permeability of the substance. Got it? Do you have any doubts? Up till now? Is there anything? Anything? Is there? No? Great. Let's have certain questions. The measure of magnetic material responding to the external field is called as the, what does it call? Yes, it's a measure of magnetic material responding to the external field that we call as the susceptibility. Next, the dimensions of the magnetization, it was the M, which we have already derived. It's a M by V. This is M, this is equals to I into A divided by meter cube. So this is equals to ampere into meter square divided by meter cube. This is ampere per meter. This would be its dimensions. I hope this is clear. Is it clear? So this was the certain basic terminologies, and these are the certain basic terms that we used to define different materials based on their magnetic properties. Now let's have an introduction with the magnetic materials that which are the materials are there and how their behavior will be when they have been placed in the magnetic field, and what properties do they contain. So let's begin then. It's a classification of magnetic materials. We have primarily we have three materials, different types of material. The first, it's the diamagnetic substances. Another is the paramagnetic substances, and the third is the ferromagnetic substances. So one is there the diamagnetic substances, the others are the paramagnetic substances, third is the ferromagnetic substances. Let's begin with the diamagnetic substances. The diamagnetic substances are those in which the individual atoms or ions do not possess any net magnetic moment on their own. So diamagnetic substances have a tendency to move from stronger to the weaker part of the external magnetic field. So they are going to move from stronger region of magnetic field to weaker region of magnetic field. Yes. So when such substances are placed in an external magnetizing field, then they get feebly magnetized. They are not going to magnetize anyway. They are going to have a feebly magnetized in a direction which is opposite to a magnetizing field, and that's why that is the field lines are repelled or expelled. In other words, this can be put as a that unlike the way a magnet attracts metals like iron, it would repel. If magnet would be there, it would repel them. It would repel a diamagnetic substances. I hope this is enough to understand this. Yes, let's look at the examples of the diamagnetic substances. Silvers, gold, all are the diamagnetic substances. Even one more examples, they are the bismuth, glass, lead, water, marbles, sodium chloride. All this are the examples of the diamagnetic materials. I hope this is clear. Is it? So let's have a look. One more very important characteristic of the diamagnetic specimen. It says that when diamagnetic sample is placed between the two pole pieces, let's have a look. This is north pole and this is south pole, and let's suppose we have one material having more property of diamagnetism has been placed over this. Then then when placed in a non-uniform magnetic field, this bar will tend to move from high to low field. That we have already discussed, that it will be having tendency to move from the stronger field to the weaker field. So we can say diamagnetic substances are the ones in which resultant magnetic moment in an atom is zero. Why? Because they are going to have a feebly magnetized. And one more thing, that the field lines are repelled or expelled, and the field inside the materials is reduced. Does it clear? Does it? Great. So this is the diamagnetic substances. When such substances are placed in an external magnetizing field, they get feebly magnetized in a direction opposite to a magnetizing field that we discuss. As well as look at this. This is the diamagnetic material. This is the magnet. If you observe this area, then these lines have representing that repulsion between these two. That means it is going to be repelled by the magnet. So when magnetic field is applied, those electrons having orbital magnetic moment in the same directions slow down, and those in the opposite direction speed up. So ultimately the situation will come that all those electrons which are in opposite direction will be having a more tendency, and all those which are having or which are moving in the same direction will be slowed down, and eventually that will stop. So this is the situation of the diamagnetic material. Look at this. One more time, it's when a diamagnetic substance, it is suspended in a freely in a uniform magnetic field. So in this situation, the rod align itself in a direction which is the perpendicular to the direction, in the direction perpendicular to the direction of magnetic field. Yes. So the most exotic diamagnetic materials are the superconductors. What superconductors is? It's these are the metals that is cooled to very low temperatures and which exhibits both perfect conductivity as well as perfect diamagnetism. So superconductors are the most exotic diamagnetic materials. In this, the fill lines are completely expelled and they are having a susceptibility in a negative. When I understand susceptibility in a negative, yes, that means they are not going to be ready to become a magnet when it has been placed in the magnetic field. So a superconductor repels a magnet, and it is going to be repelled by the magnet. It is just as the Newton's third law, action and reaction are always equal and act in the opposite direction. So the phenomenon of the perfect diamagnetism in superconductor is called as the Mensur effect, and after the name of the scientist, Mr. Mensur has demonstrated this effect, and based on that the effect has been given a name. Yes, this has been asked in the examination recently. Now superconducting magnets can be gainfully exploited in variety of situations. For example, for running magnetically leviated superfast trains. Yes, so here in this case a diamagnetism play a very vital role. I hope this is clear. Is it clear? Is it is it clear? Are you sure? So let's have certain MCQs based on this. The most exotic blank materials are the superconductors. Yes, they are the diamagnetic materials. Lead is an example of, yes, lead is an example of diamagnetic material. Now let's focus on the paramagnetic substances. When I discuss the paramagnetic substances, I understood that they are the materials in which each individual atom or molecule or ion has a net non-zero magnetic moment of on its own. So when such substances are placed in an external magnetic field, when such substances are placed in an external magnetic field, they will get feebly magnetized in the direction of the magnetizing field. Look, this is the difference between the diamagnetic substance and paramagnetic substance. If you remember the cases of the paramagnetic substance, in diamagnetism, the atoms or molecule does not have any magnetic moment of on its own. Here they are having a magnetic moment. Next, in when diamagnetism or materials having higher property of diamagnetism, when placed in external magnetic field, they will tend to, or they will align themselves from the stronger magnetic field to the weaker magnetic field, and they are not going to magnetize anyway. In this in this they are get feebly magnetized. One more thing which is very important, in the direction of the magnetizing field. So in the presence of an external field B naught, which is strong enough, and at low temperatures the individual atomic dipole moment can be made to align, and it will point in the same direction as B naught. So net magnetic field, or I should say a total magnetic field, will increase when they have been placed in certain external magnetic field. Hope this is clear. Is it? Great. So let's see to the examples of the paramagnetisms. Aluminum is there, platinum, manganese, chromium, liquid oxygen, calcium, all this are the paramagnetic substances. All this are considered as a paramagnetic substances. I hope this is clear. One more thing, it's a paramagnetic liquid in watch glass. Let's have a look. When a paramagnetic liquid contained in a watch glass is placed on two pole pieces that are lying close to each other, it shows an elevation in the middle, and when the pole pieces are moves apart, then it gets accumulated at the sides. So look at this. This was the initial situation, that this is the north pole, this is the south pole, and watch glass has been arranged in this. So when this materials are moving towards the each other, you can see the elevation. This elevation representing that they are there is an increase in the net magnetic field. Yes, did it clear? Does it? Great. So when a paramagnetic substance is suspended freely in a uniform magnetic field, this rod will align itself in a direction which is parallel to the direction of magnetic field. Yes, so they are going to add it up because it is parallel to the direction of magnetic field, while in diamagnetism it was just the subtracted and came to the zero. Yes. Now one more experiment, that if one limb of a narrow U tube containing a paramagnetic liquid is placed between the poles of an electromagnet, then electromagnet can be considered as it is the one kind of magnet, or we can say it's a specific kind of magnet which will behave as a magnet when current is flowing through it, and it is not going to behave as a magnet when no current is flowing. So if no current, it is just, we can say that it is the iron piece, and if current is flowing, it will behave as a magnet, so it is the electromagnet. So when switching on the field, when switching on the fields, look at this, the liquid rises, the liquid is rising on this limb. I hope this is clear now. So when a specimen of paramagnetic substance like aluminum or platinum is placed in a magnetic field, the lines of forces prefer to pass through the specimen rather than from air. So they are tend to adding up. So when they are placed in a non-uniform magnetic field, this bar will tend to move from weak field to a stronger field. Yes, this will tend to move from the weak field to strong field. I hope this is clear. When it was a diamagnetic substances, tend to they were tend to move from stronger field to weaker field. Yes. Now this is their relation with the temperature. Experimentally, the magnetization of a paramagnetic material is inversely proportional to the absolute temperature T. So we can say that magnetization is inversely proportional to the temperature, or susceptibility is inversely proportional to the T, and if proportionality symbol has been removed, that can be replaced by the constants. It's a C into mu naught divided by temperature. This is known as the Curie's law. Even the graph has been plotted something like this. This is susceptibility, this is temperature, so this will be moving like this. So this represents that as temperature increases, the susceptibility decreases. As temperature increases, the susceptibility decreases, and the susceptibility decreases, it means the paramagnetic substances can convert itself to the diamagnetic material if temperature is beyond certain limit. This is known as Curie's law, and the constant C is called as the Curie's constant. Thus, for paramagnetic material, both susceptibility and mu r, we call it as a relative permeability, depend not only on the material but also on the simple temperature. Does it clear? Does it clear? Great. So as the field is increased or the temperature is lowered, the magnetization increases, until it reaches the saturation value ms, at which point all the dipoles are perfectly aligned with the field. And beyond this, Curie's law is no longer valid. So up to certain limitations we can apply Curie's law to the materials. I hope this is clear. So let's again look at the certain questions, certain MCQs. Let's have a look. First, permanent magnets are made up from, they are made up from the paramagnetic substances. Yes. And susceptibility, susceptibility is small and negative, it is for diamagnetism. If it is susceptibility is small and positive, then it would be a paramagnetic material. I hope this is clear. Is it is it clear? Are you sure? Can we move to the ferromagnetic substances? Can we? Let's have a look. The ferromagnetic substances, what are they and how they will behave? So let's have a look. These are the certain examples of the ferromagnetic materials. I have put the slide at a very front of the ferromagnetic, because what I want is that you must assume that how this material should behave. Let's look at the examples. Iron is there, cobalt is there, nickel is there, it's a disoprosium is there, it's a gadolinium would be there. This all are the ferromagnetic materials. You must know all this. Iron, that is known to us. Cobalt, definitely. Nickel, yes, definitely. Not sure about the remaining two, but you must know what iron is, how iron should behave, what cobalt is, how it should behave, and something. So now there must be certain picture should be clear in your mind that what ferromagnetism is all about. Let's have a look theoretically. So when we say a ferromagnetism, we can say that they have strong tendency to move from a region of weak magnetic field to strong magnetic field, and they get strongly attracted. They are having a tendency to get strongly attracted to a magnet. Yes. So ferromagnetic materials are those which get strongly magnetized when placed in an external magnetic field, and the magnetization varies randomly from domain to domain when there is no bulk magnetization. Does it clear? Does it? So they have a strong tendency to get it attracted. Yes. And they have a domain cultures. Yes. So every domain will try to align themselves in the same direction of the external magnetic field. But this is the case when they have been placed in certain external magnetic field. Got it? Great. So look at this. It is the situation when these materials are not being placed, in any external magnetic field, but they are now free from the any external magnetic field. Now these are the atoms that themselves have magnetic properties due to the spinning of the electrons around the nucleus, and this group of atoms join so that their magnetic fields are all going in the same direction. Look at this. If you observe this carefully, that this all electrons are moving in this direction. So a magnetic momentum, or we can say a magnetic dipole moment of all these electrons is going to be added up. A same thing can be seen over here, so these areas are called as the domains, and they have a tendency to move in the same direction. Now the situation is this: when this unmagnetized substances is placed in a magnetic field, the substance can become the magnetized, and this happens when spinning electrons line up in the same direction. So look at this. Look at again carefully when we have discussed it, that here B external is equals to 0. This is the case when no external magnetic field is available, and every domain is aligned according to themselves. And but every electrons of that domains are aligned in the same direction. So electrons, every electrons of the different domains having the same direction. Now, but let's suppose this is the direction of external magnetic field in the positive x direction. So if this happens, that means if the ferromagnetic materials have been placed in the external magnetic field, then we can say that every domains will arrange themselves, or every domain will have a tendency to align themselves in the direction of external magnetic field. So that's why this will add up in the same direction, and this will make a strong and better magnet. So so look at this. This is the magnetic material, this is the magnetic material, and this is the magnetized material. Yes. So when aligned, the domains reinforce one another and create north or south pole at their either end. So normally they are arranged in the magnetic material, all pointing in the different directions in a completely random fashion, and so that their magnetic effects cancel each other when there would be having no magnetic field. Yes. So it is the analog of the dielectric constant in electrostatic. So the magnetic permeability of the substance is mu, and it has the same dimensions as mu naught. So this mu could be written as mu naught into mu r, and this mu naught would be equals to 1 plus susceptibility. Yes. Now when a specimen of ferromagnetic substances like iron or cobalt is placed in a magnetic field, more lines of forces prefer to pass through the specimen rather than from air. Yes. So this is a specimen of ferromagnetic substance. If if we rise the temperature of the ferromagnetic substance, the domain's mass may disintegrate and the substances turns paramagnetic. So this is the temperature at which this happens. This can be said as the Curie point. So thus Curie point is the temperature. Curie point is the temperature above which the ferromagnetic samples loses ferromagnetism and turns into a paramagnetic substances. So this is the reason, if you have remembered that in probably in 6th class or in 7th class, we have been magnet in our curriculum. And when magnet is in our curriculum, that when we used to have called that how a magnetization or how a magnetic property of magnet can be lost. So we have been different ways to lose the magnetic property. One was, I think, hammering was there. Another was to raise the temperature. So this all are the properties. This all are the properties. One more is that keep two same poles together. Even this all are the cases. This all are the case which will lose which will lose the property of magnetization, or which will lose the magnetic property, which will make magnet normal ion piece. Yes. So now we understood to raise the temperature what happens and why it will lose its magnetization property. I hope this is clear. So to raise the temperature, I hope this is clear. So let's back to work. It's a susceptibility above the Curie temperature. Susceptibility above the Curie temperature in the paramagnetic space, or in the ferromagnetic space, can be given as xi is equals to C upon T minus Tc, where T is greater than Tc. So is it clear? Now let's compare the magnetic materials in a one frame. So when diamagnetic material is there, when diamagnetic material is there, my lines or I should say magnetic field lines will be tend to pass through air in a more regions and less through the diamagnetic substance. Relative permeability for the diamagnetic material is less than or equals to 1, and its B is less than H. Now when I look at the paramagnetic material, more and more line will be having a tendency to pass through the specimen, and its relative permeability would be equals to greater than or equals to 1, and that's why this B is greater than H. When I see ferromagnetic material in the point of view this too, that even more number of lines than even the paramagnetic material have a tendency to pass through the material, and that's why this B is much greater than H. And mu r, its a relative permeability, is much higher. We have one more relation, that mu r is equals to 1 plus susceptibility. So when susceptibility in this case is less than 1, in this case susceptibility would be less than 0, it would be in negative. In this, when we talk about the paramagnetic material, susceptibility in paramagnetic material is greater than 0, but this is positive, but this is not a very large value. Yes, but when we talk about the ferromagnetic substances, the susceptibility is much higher than the one. I hope this is clear. Is it clear? Is it? Are you sure? Yes. One more thing I need to discuss is that when we say any material is diamagnetic, when any material is paramagnetic, any material is ferromagnetic, it means that let's understood this, that what paramagnetic or what ferromagnetic or what diamagnetic, when we say, what does it mean? That when we say that, let's take a right over this, that let's suppose this material is there, this contains a 70 percentage of property of diamagnetism, 20 percentage property of paramagnetism, and 10 percentage properties of ferromagnetism. That means we must be sure that this is a material, this is a material which is going to repel from magnet. Yes, let's take one more example. This is a material, this is having a ferromagnetic property of, let's say, 95 percentage, a paramagnetic property of, let's say, 3 percentage, and diamagnetic property of 2 percentage. So we can say this is very good magnet. I hope this is clear what I mean to say. Yes, so this diamagnetism or paramagnetism or ferromagnetism, in reality these are not the materials, these are the properties of material. We can say that even one statement is very famous about the diamagnetism, is that diamagnetism is universal. Diamagnetism is universal property of matter. That means every material of the earth is having a certain segment for sure of diamagnetism. It is only the matter that how much, in a total of 100, how much is the percentage of diamagnetism in that particular matter. If it is higher, it is not going to be a good magnet. If it is much lower, but ferromagnetism is higher, that means it will become a very good magnet. I hope this will remove any misconception that this is material, and sorry, these are the materials and this is not the property. Does it clear? Great. So we understood that liquid and gases never exhibit, yes, they can never exhibit ferromagnetic properties. because they cannot have anywhere domain structure. Second, ferromagnetic ore properties are due to this properties are due to it is due to partially filled inner subshells. Yes, so let's just wind it up the session over here. After so many lectures, this is the lecture where we have not a single numerical. Yes, from where we have begun the first unit, electric charges and fields. This is the first lecture where we do not have even a single numerical. Yes, but this is the complete theory session, but this contains a very high amount of information that almost every slide is having containing at least a single question. So please go through this very carefully. This is very important because when theoretical questions has been asked in the examinations, this is having a two advantage. One, it does not take any time, and second, it does not have a probability to have an error. Yes, because accuracy is not required. We know this, we are going to take it, and that's it. It is a correct. We don't know this, we are just going to omit it. That's it. There are not chances that it may be right, it may be wrong. If silly mistake is there, it would be a wrong, and every kind of stuff has been removed. And biggest benefit is that it will save a time so that we can do any other questions. This is the biggest benefit of the theoretical questions. Please go through this. This will help us. Thank you. Have a good day. Take care. Bye bye.